central tendency. So today's agenda is as follows. What are measures of central tendency? How do we describe the data numerically? Which are the measures of central tendency? In particular, we will look into the mean, weighted mean, median, mode, geometric mean and harmonic mean. Some examples and merits and demerits of each of these measures of central tendency and a little knowledge check. So let us begin with our journey into the subject of statistics. As we know that statistics deals with data. Data is a huge set of numbers and one has to come to know what these numbers try to tell us. And this is true in every walk of life. So basically, if you don't know statistics, then without statistics, it is like the tale of elephant and the seven blind men. I am not going to recite that tale over here. The picture is pretty much clear that all these blind men are trying to understand what an elephant is like. But since they cannot see the animal in toto, whatever part of that animal they are at, they are trying to describe the elephant according to their own experiences. So someone at the leg of the elephant is saying that it's a tree. At the trunk, the fellow is calling it's that it's like a snake. At the tail, the person is calling it like rope and fan and wall and whatnot. So it's very funny because we are calling it funny as we are able to see the complete elephant and therefore we can ridicule each one of them. So the same thing happens if you get only a snapshot of the data or a part of data, or if the human mind or human brain is not able to comprehend the data in its entirety. So basically, in order to get the data, first of all, we have to collect the observations. That is why Galileo had said in the 16th century, when he was studying the celestial objects, measure, 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 measure again and again to find the difference and the difference of difference. So unless you measure, you won't be able to compare the things with previous, with others, etc. So basically, the data we want to get the essence of, or we want to make the sense out of the data. So what is required is that instead of huge amount of data, we want to get some number which will be a representative of the data. That is what is known as measure of central tendency. Here, I would like to demonstrate to you in simple manner. So look at this spreadsheet. Here, if you look at this data, then this is the data about weight of 100 patients whenever they were enrolled in the clinical trial in kgs suppose. Now just looking at this data, are you able to tell anything about those values? I mean, it doesn't make sense. Or if you are very good at numbers, then you will be able to tell something that, oh, they seem to be two-digit numbers. That's the only thing I think one will be able to come up. Or they are around something 50 or something kgs like that. So that happens with if you are looking at the data and not summarizing it. So in statistics, we want to summarize it in some measure. For that purpose, first of all, we classify that data into a frequency distribution. So here, if you look at the lower part of the spreadsheet, here is the frequency distribution of the data. Before that, if you observe that I have computed the minimum of the numbers and the maximum of numbers, which has helped me in coming up with the different class intervals. So those who have weight up to 35, then between 35 to 40, between 40 to 45, and so on and so forth. This frequency column gets me the number of patients having weights in that particular class interval. Okay. Now when you draw the histogram, which is a statistical diagram like this, then these bars represent the frequencies of the respective classes. So you see that initial bars are very short. The middle one is taller. Then again the bars go on decreasing, the frequencies go on decreasing, and in the end 65, that last class, is having a very short bar. So that means you will observe that the numbers are tending towards center from right as well as from left. So here in any kind of data you observe this kind of tendency to cluster around some central value. So that tendency in the data to cluster around some central value is known as central tendency in the data. And this is generally observed in all variables, in all aspects, whichever variable you will try to measure. Now it may happen that these bars might shift, that means this one can be here as the second bar and then go on decreasing like that. So these kind of shapes, you will come across different shapes, but one thing would be sure, that if you are taking the observations from a single population, then there will be a tendency that the frequencies will go on increasing up to a certain point, and then the frequencies will start decreasing further. Okay? So this kind of tendency is known as central tendency. So basically we want to find out a single value that attempts to describe a set of data by identifying the central position within that set of data. These are called as measures of central tendency. So today we will see some such measures of central tendency. These are mean, median, mode, then combined or weighted mean, geometric mean, and harmonic mean. Whenever we want to describe the data numerically, or we want to get the representatives of the data, and then we are looking through the data, the center location or measures of central tendency are depicted over here. After that, we will be looking into the locations which are known as the partition values. These quartiles and percentiles are known as partition values. And then we will further study what is meant by variation or spread in the data. So this slide is just to tell you what all other things we will be doing into the descriptive statistics. But currently we are focusing into the leftmost branch of this numerical description of the data. So the first measure of central tendency, which is also called as average, is the arithmetic mean. If you are given a data, so you know, everybody knows the average marks scored by you in different subjects. Suppose there are 7 subjects, then each one of us has computed the average marks. So that is it, that you have to take the sum total of these numbers. If there are 7 subjects, you will take the total of the 7 subject marks, divide by 7, and you will get the arithmetic mean or average. So that is the arithmetic mean, or in simple language we call it as average. In case of group data, like this is what is known as group data. So here, if you don't know the exact numbers, here we know them and then we have classified them. But suppose you don't know and you have only this frequency distribution, then you will compute the arithmetic mean by multiplying the frequency with the midpoint of the data, midpoint of the class interval. That is called as class mark. So in this case, here the class is from 30 to 35, so it will be 32.5. Here it will be 37.5. So it is obviously an approximation to the true arithmetic mean. But there are some instances where you have directly the group data and you have to compute the arithmetic mean. So the formula for group data is, in the numerator you will take the product of class midpoint and its frequency and take the total of all. So as if you are taking the total of all the observations divided by total frequency. So again it is the total number of observations in the data. So this is what is known as the arithmetic mean for frequency distribution, or it is also known as weighted mean. This is one simple example. Calculate the arithmetic mean of marks scored by a student in 7 subjects, and the marks are 61, 68, 69, 70, 63, 60, 78. So just by looking at the data, if you don't compute the arithmetic mean, what at the most you can say is that this fellow has scored first class because all his marks are beyond 60. When you compute the arithmetic mean, you will get exact idea about its percentage or average marks as 67%. If there are two groups of data, such as here, for example, you have arithmetic mean of weight of 100 boys as 50 kg and arithmetic mean of weight of 50 girls is 45 kg, then how will you compute the arithmetic mean of combined group of boys and girls? See, whenever you are computing the arithmetic mean, in the numerator you have to take the total of all the observations. So how will you get the numerator here? You will multiply the mean of boys by the total number of boys plus mean of girls by the total number of girls divided by total number of people, that is including girls and boys, and therefore the combined or weighted arithmetic mean comes out to be equal to 48.33. So this is a simple illustration of that. Now before going into this next measure of central tendency, let us see how to see what happens with the mean. See, this is the data. Okay. Now here the number of observations you observe are 13 and the arithmetic mean is equal to 18.62. This is some data, could be a weight of some animals, and here you observe that there is one observation as 100 which doesn't fit into the other observations, the class of other observations, because all of them seem to be around 12, 14, 2, 5, 7, 9, 11, and suddenly there is this observation. In statistics, it is called as an extreme observation. So, if suppose this observation is wrong and suppose it is truly 10, then the arithmetic mean changes to 11.69. So this could be the true arithmetic mean, whereas because of the wrong observation taken here, the arithmetic mean has changed to 18.62. The point which I am trying to make here is that the arithmetic mean is sensitive to the extreme observation. If you have a few observations which are very high or which are very low, for example, if wrongly someone has typed here in place of +9, someone has typed it as -9. Then and this was 10 in true sense, and then it comes out to be equal to 10.30. So is this a proper representative of the data? We will say yes if we have a data like this, a very nicely behaving data. It is spread only between 30 to 65 and the variation is not much, and therefore the arithmetic mean which is computed here is 50.34. So if you remember, this was the data of weight of 100 patients and the average weight of a patient here is 50.34 kg. So which makes sense, isn't it? Which makes sense. This makes sense because this data is free from extreme observations. Therefore, arithmetic mean is good enough if we don't have extreme observations in the data. Otherwise, we have seen what has happened here. So then in order to remove the problem of the extreme observations impacting the measure of central tendency, one should come up with a different measure which will not get affected by the extreme observation. So there is another angle to look at the data. See, while computing arithmetic mean, we tried to take into account each and every observation in the data and give its own weightage and computed the total and divided by the total number of observations. Another way to look at the data is that I want the central observation. I don't want the average of it, but I want the central observation in the data. So that central observation, if you are looking at, then you are looking at or finding the median of the data. So median is defined as the middle value of the data, obviously when the data is sorted from lowest to highest value or highest to lowest value, either way. This is a funny picture here. These are having different sizes of the shirts, each one of them is wearing, and you see that the median is the M whenever you are arranging them in the ascending or descending order of the sizes. So because there are extra small, small, medium, large and extra large sizes, therefore they are arranged into the ascending order and then you take the median as the middlemost. So this is the way one computes the median of the observations. Now see, let us see what happens when we look at the data. So look at this data, which is the same data arranged into the increasing order of their magnitude. So there are in all 13 observations. So when you arrange them into increasing order of magnitude, which is the middlemost observation? 13. See, 1, 2, 3, 4, 5, 6, 7. Is that right? This is the middle observation because here below this observation there are 6 observations and after this observation also there are 6 observations. So 50% of the observations in the data are below this number, 50% of the observations above this number. So this is called as median and that is the central of the data. So median is 12 here. So here it is computed as 12. Now look here, suppose I change this 100 number as 1000. Is it going to affect the median of the data? No, because the position of the median remains at the 7th place whenever you are ordering them in ascending order. Or here, even for that matter, if I change this 23 to 230, then also the median remains the same. But if you compute the average of this changed data, then you are going to get such a number 103.769. So this is, will we call this as a representative of the data? The answer is no, because most of the observations are around or below 21. So therefore 103 cannot represent the data and therefore median is better than mean. So in some such situations, whenever you know beforehand that the data is going to get affected by extreme observations, you will not go in for means, or if you want to stick to mean, then you will remove the outliers. We will see what are the outliers and how to take care of them in our subsequent sessions. But then you will definitely consider the median of the data. Now, this was a simple example whenever we had 13 observations in the data. What if I have 12 observations in the data? That means even number of observations in the data. First of all, I have to arrange them in the increasing order of magnitude. So let me sort them. Okay, so this is the data sorted. Now if we try to find out the middle observation, I don't know which is the middle observation. 1, 2, 3, 4, 5, 6. This is one middle observation. Let me highlight it. But then there are 5 observations below this number and 6 observations beyond this number. So this is not central observation. What is central here is the pair of observations. So 12 and 14, this pair is the central pair in the data, because below which there are 5 observations, above which there are 5 observations. So while computing the median of the data which is having even number of observations, what is done is that you first of all identify the middlemost pair of observations and then take the average of those two numbers, that is mean of those two numbers. So what is the mean of these two numbers, 12 and 14? Obviously 13. Okay. So here the median is equal to 13. So when there are odd number of data points, the median is the middlemost point. When there is an even number of data points, the median will be the average of the two center points. So following are the temperatures recorded in certain city over a week. These are the temperatures in centigrades. Seems to be a very hot city. And what is the median value? Don't forget to arrange them in increasing order. That's generally a mistake people do. Don't just take the middlemost observation. First arrange them in increasing order and then find out the middlemost observation. So median is equal to 37 degrees. Sometimes we are not interested in the central observation. We are neither interested in the center of the data, which is provided by the mean. We are nor interested in the central observation so that it divides the data into equal two halves, but we are interested in the most typical observation in the data. For example, if you are talking about the number of children in a family, does it make sense to compute the average number of children in the family, that is arithmetic mean? First of all, it would come out to be equal to something as 3.7, which will not be a true value for the number of children in the family. Then it doesn't make sense to take the arithmetic mean, because some families may have number of kids to be around 7 or 8. So quite an extreme observation, but such families will be rare. So all sorts of problems are there. At the same time, median also doesn't help, because you are going to find, so if you compute median number of children in a family, then 50% of the families are having children less than that. 50% of the families having children more than that. Also doesn't make sense. Median makes sense whenever you are talking about the median income. So in the reports you will see it's always median income is reported than the average income or anything like that. So what is the way out in such cases? The way out is that there is third measure of central tendency, that is mood. So most typical observation. Generally people, when we ask the question, how many children are there in an Indian family generally? And suppose the answer is 3, then we will say that the mode is 3. So mode is the most frequently occurring observation or the most typical observation. So here it is depicted in a very colorful manner. There are 3 red balls and 1 purple, 1 blue, 1 navy blue. Red seems to be more common. Okay. So this particular observation is the mode. Again, there is one point of caution, is that mode is the most frequently occurring observation. It is not the frequency that you are talking about. For example, if the frequency of the observation is 6 and the observation is 3, then the mode is not 6, the mode is 3. Okay. So mode is the most frequently occurring observation. Now there can be more than one mode of a data set if more than one value occurs the most frequent number of times. So there can be two maximum. That's kind of situation here we are talking about. So mode may not be unique. So that is one of the demerits of mode. For example, find the mode for the following list of values. You see that the number 13 is repeated maximum number of times. See, 13 is repeated how many times? 1, 2, 3 and 4. 18 is repeated only once, 14 is repeated twice, 16 repeated once, 21 repeated once. So if you compute the frequencies, the frequency of 13 is 4 and that is the highest, and therefore the mode is 13. So here, although you will find it quite repetitive, but here if you look at this data, then find out the value which is occurring maximum number of times. So 14, here is also 14 and no other value is repeated, I suppose. Yes, no other value is repeated, so the mode is 14. Then you will say that if every number is, for example this 14 is some 19, okay, then every number is unique here, then which is mode? So for such data set, we say that mode doesn't exist. So mode doesn't exist, a kind of situation can be there, or there can be several modes also. For example, you may have here 14, so 14 is repeated twice, and this is also suppose 15, then 15 is repeated twice. So you can say that 14 and 15 are the two modes of the data. In such cases, the distribution is called as bimodal whenever there are two modes. Okay, so having talked about the main three measures of central tendency, arithmetic mean, median and mode, and there basically the merits and demerits and the situations whenever which is used, you will find that most of the times arithmetic mean is used, even though we have talked about its demerits as being impacted by extreme observation, etc. One important reason for using the arithmetic mean most of the times is that it is amenable to further mathematical treatment. So further statistical analysis can be very well done with the arithmetic mean, which is not the case with the median and mode the least. If you are working with the non-parametric inference, then median is used. If you are working with parametric inference, then arithmetic mean is used, but mode is rarely used in statistical analysis. For reporting purposes, it is a very good and crude measure to give the insight of the data. Then there are some two other measures which are geometric mean and harmonic mean. We will not go into much of the details of these means, but since some SAS procedures do give these as the outputs, and in some situations they are having an edge over the arithmetic mean. For example, if you are trying to estimate the changes in some kind of quality, then you will be talking about the geometric mean. So what is geometric mean? See, when we computed arithmetic mean, we took the sum and divided by the total number of observations. While computing geometric mean, we take the product of all the observations and take the kth root, if there are k observations, kth root of the product. So this is helpful whenever we are making the log transformations of the data and computing the arithmetic mean of the log transforms. So you just have to take the product of all numbers and take the kth root if there are k numbers. Obviously, since you are taking the product of these numbers, 0, if one of the numbers is 0, then the product is going to be 0. So the numbers cannot be 0, then the number cannot be negative also. So the geometric mean only works with positive numbers, Negative numbers could result in imaginary results depending on how many negative numbers are in a set. Right now you don't have to bother much about that. You just have to keep at the back of your mind that there is something called a geometric mean which is used sometimes. Just as an illustration, if your numbers are 1, 2, 3, 4, 5, then what you will be doing in computing the geometric mean is that you will take the product of these numbers and then take the fifth root, that is raised to 0.2, and the geometric mean comes out to be equal to 2.60. This is also affected by extreme observations as arithmetic mean gets affected. This is also, whenever you are talking about the rates of something, rates or ratios of something per unit of monetary value or speed, you are computing the harmonic mean. So there also you will not go into the details of harmonic mean, how is it better than arithmetic mean and all, because this will also be rarely used. But sometimes there will be situations where harmonic mean is a necessity. So how is it computed? Look at the formula. See, x1, x2, xn are your observations, and you are taking the reciprocals of these observations, and then take the sum of the reciprocals, then compute the mean of the reciprocals, and then again take its reciprocal. So it is a kind of jugglery that you are making to compute the harmonic mean. So basically it is the reciprocal of the mean of reciprocals. That is how we call it, and it is easy to remember it that way. So it is useful for quantitative data. So here is an example and the situation also, that the distance from my house to town is 40 kilometers. I drove to town at a speed of 40 kilometers per hour and returned home at a speed of 80 kilometers per hour. What was my average speed for the whole trip? So whenever you are computing the average speed kind of thing, then it doesn't make sense to take the total distance divided by the time. That doesn't give you the average speed. But if you compute the harmonic mean, we will compute it like this, that you take the values 2ab, you compute the speeds first of all and then take the harmonic mean of the speeds. So the formula is 2ab divided by a plus b. So a is 40 and b is 80, and then you get the harmonic mean as 53.33 kilometers. You can try yourself what will be the arithmetic mean of the data and compare it with the harmonic mean. Exercise for you. Just let us browse through the merits and demerits of each of these measure of central tendency. So mean, easy to understand and calculate. It's very rigidly defined. Basically, if you have a data, then your mean and my mean will not be different. They have to be the same if they are computed correctly. It is based upon all values in the given data. It is capable of further mathematical treatment. It possesses sampling stability. What does it mean? It's little hard at this point of time to understand this concept. But in short, if you are taking several samples from the population and computing the arithmetic mean, and if the population is homogeneous, then your sample mean will not vary much from the other samples. Okay, so that is what is meant by sampling stability. On the other hand, the demerits of arithmetic mean is that it is applicable only for quantitative data. How will you find out the arithmetic mean of colors? Yellow, purple, red, orange, green? Not possible. Cannot be calculated for the data with open-end classes. If you have a classified data, frequency distribution, with first class as below 30 or whenever it is income above 10,000, then the problem is that you can't get the class mark and therefore you cannot find it. It is unduly affected by extreme values. At times mean may not be an actual observation in the data that we have seen. It cannot be determined graphically, but the median can be determined graphically from the cumulative frequency curve. Here are the merits and demerits of median. Median is also rigidly defined. It is easy to understand that 50% of the observations lie below, 50% above. Since it is a positional average, it is called as positional average. It is not affected by extreme values. Even if extreme values are not known, you can compute the median. So for open-end classes, you can compute the median. It can be located just by inspection in many cases graphically. It can be calculated for data based on ordinal scale. What is an ordinal scale? It's a qualitative kind of scale. For example, if you consider the severity of the drug, then not at all severe, 0, then mild, then medium, then high and very high. Suppose these are the scales of severity, then obviously the medium one will be called as the median here. As against these merits, the demerits are not based upon all values of the given data. Obviously, if you don't want it to get impacted by extreme observations, then this demerit is definitely going to come, because you are not worrying about what is going to happen at the end of the data. For larger data size, the arrangement of data in the increasing order is difficult process, which is actually not the problem now with the computers and programs, but still it is not manageable to look through the data if it's a huge data. Not capable of further mathematical treatment. This I mentioned that statistical analysis is heavily based upon calculus methods, and wherever you have to compute the derivatives and integration, and median is not amenable to that, whereas arithmetic mean is very much capable of handling that. Insensitive to some changes in the data values. If you alter some of the values, then the median doesn't alter. So one drawback, the merit becomes the demerit and demerit becomes the merit. So that is the situation happening here. Mode is the crudest measure, easy to understand and calculate, not affected by extreme values or sampling fluctuations, because it is the most typical value which is occurring with the maximum frequency. Even if extreme values are not known, mode can be calculated. So some of these merits are obviously common with the median, can be located just by inspection in many cases. If you just look at the data, it's a huge data, and if you see all the time occurring that 100, 100, 100, 100, you will come to scream like that 100 is the mode, right? Is always present within the data. It's a value which the data observation can take, applicable for both qualitative and quantitative data. It's the most important merit of mode. So mode, the meaning of mode in English is actually fashion. So most popular thing people are wearing, so like that. Most popular car people are using, that is the mode. Demerits is not rigidly defined. There can be two modes, their mode cannot exist, not based upon all values of the given data, not capable of further mathematical treatment, if is indeterminate if the model class is at the extreme of the distribution. So these are some instances where mode is of no use. Similarly, there are merits and demerits of geometric mean. Most of them are common with the arithmetic mean, the merits at least, but the demerits is that calculation is rather difficult, not easy to understand, and may not coincide with any of the observations. Similarly, the harmonic mean, it is capable of algebraic treatment. Basically, these are context specific. The arithmetic mean and geometric mean are context specific, and therefore they are not very much in use. Before going in for the knowledge check, I would like to bring to your notice the SAS procedure, proc means, used to compute these measures of central tendency for a certain data. So there was an data which is of hypothetical nature. This is that data. So here this observation, patient ID, and there are treatments A and B. See, treatments A and B, and then you have central, so this multi-centered clinical trial, so center 1, 2, etc. Gender, age of the patients, response, severity and score. So here we have computed the using proc means. All of you I suppose are aware of the syntax. So proc means data clin trial, and you are asking that procedure to compute the number of observations, mean, median, standard deviation, minimum, maximum, range, then lower confidence limit, upper confidence limit with the decimal accuracy equal to 2 by treatment. Because of this by treatment, you are computing it separately for treatment A and treatment B. And for the variables, score and age. And this is the output. So, for variable score and age, total number of observations, the arithmetic mean, this is for treatment A. So, mean is 26.48 for the score, which is the severity score. Median is 20, so there is a difference between mean and median. And standard deviation, minimum, maximum, we will see in our next lecture what is meant by standard deviation and how to compute that. Similarly, for age, the mean is 43.40, but the median is 42, and so on and so forth. So let us return to the knowledge check and try to answer this quiz. Arithmetic mean is the ideal average. Is it true or false? Median is the positional average. Arithmetic mean can be determined graphically. Median can be determined for qualitative data. Mean median mode always coincide. Mean lies between the smallest and largest observation. I think you will be able to answer all these questions. Only thing is that arithmetic mean, other measures we haven't shown that they can be determined graphically, the median and mode, but they can be, and therefore arithmetic mean cannot be determined graphically. So this statement is false. With this, we end the session on measures of central tendency.